Mr. Aaron, Mr. Ryan, are you alright? Okay. So we're going to talk about the binary tree, converting the binary tree to undirectional graph. Okay. So remember, all these are graph, right? But only the first one is the tree. Okay, and specifically it's binary trees. So the binary trees, first of all, it's a graph. It's a subset of graph, right? And it doesn't have these errors. Okay, it doesn't have error. It's undirectional graph. Okay, but some people will think it's a directional. It's DAG. Why is that? Because the parents from the trees, we can only if we're given a root of tree, the root of the tree, we can only visit from parents to kids. Yeah, we can't go back, right? If you're given 2, you don't know where the parent is. You only know it's kids, right? So sometimes we can think of trees as directed from parents to kids, and acyclic. Yeah, acyclic. What does it mean? Acyclic. What does this mean?
That it goes around.
Acyclic. Cyclic means the round and round. Acyclic. What does it mean?
It means that it goes round like.
No. Directly acyclic.
Oh, then no.
No, the opposite. The opposite.
No.
Graph. Okay.
But if you raise this.
Yeah. It means goes round and round. Okay. So look, this is not a tree because it has a graph. It has a cycle, right? We don't have a cycle in the tree. And this is not because it's not connected. It's not connected, right? These two are separate. This is not connected. This is kind of forest, right? Forest is multiple trees. Right? And this is.
That is a small tree.
This is not, right? If we okay. So this is the directed graph. Yeah. Undirectional graph means that it just it doesn't have errors. Yeah, it's just like that, right? So it means 3 can visit 4, 4 can also visit 3, okay? Right? So we are going to convert the binary trees, okay? Convert the binary trees. A binary tree, it means that a parent can only have 2, maximum 2. Yeah, if it doesn't have any kids, it's a leaf node. We call it terminal node, okay? Terminal node, okay? Leaves. Okay, so usually, how can we represent a tree? Class tree, yeah, we cover tree, and then define. Usually we define a tree using this kind of structure, yeah. And the value and the left and right, okay. Yeah, so self dot value equals value. That means the value of the node, and then it has two things pointing to the left and right. Left self dot right equals right. Okay, so this is the tree definition. One of the tree definition in object-oriented programming in Python, right? Because we have a tree, we have a node, we have value, and we point to the left and points to the right. Okay, yeah, make sense? Yeah. And also, sometimes we can define a tree like we defined a graph, which is what? Which we, for example, like this one. Look, 1, 2, 3, 4, 5. So we can define it as the list of a list from parents to the kids. A list of the edges, right? We can define it as a list of edges. So what the tree is defined is, look, it's 1 to 2. Okay, a list of these, yeah, and then 1 to 3, 3 to 4, and 3 to 5, right? You see, this is another way of defining a tree, right? And we can also use this to define a graph, right? Because the tree is a graph, right? Alright. Okay, so how do we define the graph? Remember. Define the graph. How do we represent the graph? For example, like how do we represent this in a graph? Okay, how do we represent this in a graph? 1, 2, 3. Any idea? I mean, we talked about this before, yeah. How do we define? What did I just say? If we're using this, how do we define? We just list the number of edges. 1, 2, yeah? And then what? 1, 3, yeah? If it's an undirectional graph, yeah? And then 2, 3, okay? Okay, this is undirectional graph. If it's a direction, then this, we can also use this to use the direction, yeah? Direction, okay? And sometimes if there are numbers over the edges, we call it weight, right? Because for example, if from 2 travel to 3, it costs like 5 pounds. Okay, I put a 5 here.
5 pounds?
Yeah, something like that. Yeah, if 1 to 2 costs 3 pounds. Okay, so look, this is directional weighted edges, directional weighted graph. Okay, if an edge has the numbers on it, it means the weighted.
And the 1 to 3 costs.
Yeah.
What about 1 to 3?
I don't know, maybe it's 3, okay? To make it up. So look,
3.
we can use this there from 2, and we can have another value called edge. 1 to 2 is 3, yeah, cost 3, yeah. Something like that, right? The list of edges. Alternatively, we can have this kind of data structure which calls the adjacent list. Okay, what does that mean? It means that look at taking this for example, yeah, 1 to 2, 2 to 3, and maybe 1 to 3. Okay, so look, let's say the first graph. Okay, the first that we can use the dictionary graph. Yeah, dictionary. Okay, dictionary. G, default dictionary, yeah? And then the key is the node, the vertex, yeah? This is called vertex. Remember, the vertex. Okay? Vertex. The graph is a collection of vertex and edges, yeah? So G equals a collection of V and E, okay? So G, collection of V. V is the key which is 1, and then we can point to a list of the vertex it points to. In this case, is 2, and then 3, right? And then if 2, because we have weights on it, if this is unweighted, we can just do this a list of vertex. And if it's weighted, then we can put a tuple, yeah? Remember the tuple. 2, it points to the 2, the weight is 3. It points to the 3, it weighs as 3, okay? Okay, so look, the second vertex, it points to 3, yeah? It points to 3. The weight is 5. Okay, any other vertex it points to? No, right? And then vertex 3. Look at the vertex 3, it points to nothing, right? So we do this, just an empty list. Right, so this is the adjacent list. Okay? And we also can represent the graph using the adjacent metric. So what does it mean? Look, if these are 1, 2, 3, okay, let's make it 0, 1, 3, 1, 2, okay? 0, 1, 2, so we can just save space on the metric. So look, so we can do a metric, yeah? So the rows, this is the rows, this is the columns. So for each row, look, this is G. If Gij, right? Gij means the vertex I to vertex J, right? The list, look, and the weight on it, if it's weighted. Yeah, so we can do this. G0 to 1 is 3, so we put it 0. So let's just put it, because look, there are three nodes, so there will be 3, 3, right? 9 values. So what's the diagonal? What's this bit? What does it mean? It means GII. What does it mean? The vertex I to vertex I, right? Yeah. So usually it will be the values that Okay, so the value 0 to 0, so it will be 0, right? Okay, let's fill this 0 to 1, which is 3. 0, 1. So I put this into 3. Change this to 3. Okay, and then 0 to 2. From 0 to 2 is 3. So look, 0 to 2 here. I change it to 2, right? Okay, and then 1 to 2 is 5. So 1, yeah, 2, 0, 1, 2 is 5. Okay, and one less. 0 to 2 is 3. So where do I put it? Where do I put the 3? 0 to 3. 0 to 2. 0 to Okay, wait, that's a mistake. 5 is 1 to 2, right? 1 to 2. And 3 is 0 to 2. 0 to 2. I put it already, okay? And
but if 1 to 2, 1 to 2, then what's 0?
so it starts with 0, okay? 1 to 2, yeah? 1 to 2, yeah? So look, 0, 1, yeah? 0, 1, 2, 5, okay? So there are 3 values.
This is 0.
Yeah, 0.
And then 2.
Yeah. Because look, the metric, the array, the list in the computer starts with 0. 0 to 2 is 3, yeah?
Yeah,
0.
written 2.
So okay, 0, 1, 2. Okay, 0 to 2 is 3, yeah? You're right, yeah? Okay, so what's 3? 0 to 1 is 3, okay? So there's no 2 here, right? Because there are 3 edges, 3, 3, 5, okay? 3, 3, 5. Well done, yeah? You see? Adjacent metric. This is how we represent the graph using adjacent metric. Okay, so this is just the basic, okay? Then today's task very simple. Okay. So today we give you a binary tree, yeah? Specific, but we can extend this to a general. It doesn't have to be binary tree, yeah? It could be n3. How do you say the tree which has the maximum 3 nodes?
I think it's
Ternary 3 or
I
what?
think it's maybe 3. I know.
Ternary? Is there a word called ternary?
I think it's begins with N or something.
Okay, ternary tree maybe? I don't know, means 3, yeah?
Nanary.
Okay, I don't know, okay. So look at the binary tree, okay? 1 to 2.
Navy. Naviness. Navy.
4, okay, let's say this binary tree. Yeah, this binary tree, look. This binary tree. We want to convert it, yeah? We want to convert it to a graph, like what the adjacent list, for example, adjacent list, okay? A G equals the graph. Okay, a dictionary, yeah? This is called using dictionary. And then you need to tell me which is what? 1, the 1 points to 2 and 3, okay? Yeah? Huh? But again, 2 points to 1, right? Because look. The graph, the tree only 1 points to 2, but the graph is undirectional graph, okay? So 2 needs to point to 1 again, right? Yeah? So if you take this, if you consider this as a graph, it's not a tree. Look, 2 is connected to 1, is that right? Okay, so now 3, you tell me what should I put here? 3, what should I put here? Put it in the list, what should I put?
You should put 4. No, wait.
How many vertex does the 3 connect to?
1, 4, 5.
Yeah, well done, okay. Let's go into what's a Pokemon card, yeah, if I get it, yeah? Okay? And then 4.
4 is 3.
Okay, and then 5.
3.
Okay. You see? So look, we converted this to undirectional graph because 1 connected to 3, 3 also connected to 1, right? Yeah, undirectional graph. Binary tree, you can use this, the thing we just said. Each tree node has a value, has a left, has a right, okay? Okay? Yeah. But before we do this, this is one kind of tree structure. And how about the edges? Like let's say we have edges from 2 edges. This is edges. This is the edges. List of edges. Yeah. List of edges from 2. Okay. Yeah. Okay. So yeah, makes sense. So how do we do it? Remember? For this one, it will be simple, yeah? We go through the list. I know we can just assign it, right? Yeah? But for this one what? It's not given, the tree is not given by edges. It's given by the nodes, by a root node, right? Right? So we need to traverse the tree. So what kind of argument in your mind can we use to traverse?
Search deficit.
Well done. Backward search and backward search. Oh, but first of all, let's do this, okay? That will be easy, okay? I'm going to write. I'm going to keep this, okay? This is the graph. This is the adjacent metric. Adjacent No, adjacent list. Okay, adjacent list. Yeah, because the keys and the vertex. The list is the list of the vertex it connects to, right? So, okay, so let's write this. Okay, define. Let's say convert a tree. If the tree is given edges, okay, let's write this version. First of all, we need to define this. G equals what? Default dictionary. Yeah, because by default is the dictionary. And then the default value, the value is the what? What type of the value is this the dictionary? What's this?
That is.
What's this? What's this? What's it called?
Keys values.
Yeah, but what's this? What's type of list?
List.
Yeah, list. So I put a list. Yeah. You see? Yeah. If it's an integer, we put it in. Right. If it's a string, we put a str. Right. And now we just go through the digits. For A, the edges is given A to B, yeah? A, B in edges. Then I can say G, A, well, list of edges. G, A dot append B, right? And can you write this? G what dot append what? And that will be if the given this.
B.
Yeah?
A.
Well done. Because A to B, that means there's an edge from B to A, right? Because we are trying to convert the trees into undirectional graph, okay? Yeah, undirectional graph means the both ways. Yeah. So this is the given list. It will be very simple, yeah. We just go through the list. And how about if we are given this as a root, right? We go into the root, right? And this we can't use this anymore, but. As we said, depth search, breadth search, right? But so look, if I want to travel like that, okay. Breadth search. What's the breadth search? Let's say here. What's the breadth search order for this one?
1, 2, 4, 3, 5, 6.
Level by level, okay. What's the breadth search? Depth search. If it's a pre-order. No. If it's what? If it's in order.
It's 1, 2, 3, 4, 5, 6.
Yeah. Oh, is that No. This is not binary search tree because look. Yeah, it's not. But look, it's pre-order. What's pre-order? Node left to right. We visit the node first. And we visit the left and we visit the right. Okay, so node. So we visit the node first. So it's 1. Okay, 1, 2, 3, and then visit the right. Right, which is 4, 5, 6. Yeah, node the left art. Okay. Okay. So but we visit these. So whenever we visit the node, we want to add the edge from the kid to the parent. What does it mean? What does it mean? Look, we're traversing the tree, but we want to add an edge between the kids to the parents. So what does it mean? Do we? But we don't know the parent, yeah. But we know where it comes from, right? Yeah. So what does it mean? The depth search we need to pass down the parents, right? Yeah. Define depth search. First of all, will be root, and then will be parent, yeah. Parent. What you doing? Why you're busy? Huh? Root and parent. Okay, Eric. Why do we need a parent? What did I just say?
Because the parent is.
Yeah. Why we need a parent in depth search?
Because we start from a root, which is the parent.
Yeah, and then we will go down. We want to add the edge from parent to the current, right? Yeah, that's why. Okay. Look, if not root, okay, if we reaching the empty air, we just return, right? Okay. And then if parent, yeah, if there's parent, if we has parent, because we have to check. Why is that? Because the parent could be none. In what cases the parent will be nothing? Will be none.
No tree.
The root, right? The root. The root doesn't have parent, right? Yeah. If there's parent, then we can just say G parent dot append, and you can write this as a plus equal. Okay, this is the same thing. Root, right? Okay, can you tell me what's next? G what plus equal what? Okay. I'm adding a edge from parent to the root. And what's next? Okay, come on, you're listening. If I add the edge from parent to the root, what does it mean? Do I need to add the edge from what? What should I put here?
No.
I have already added edge from parent to root, so what do I need to add next?
And you need to add
Okay, I already added edge from 1 to 2. So what should I do next? What should I add?
you add the other parts.
Okay, so what the other part is?
Root or left.
Root, there's no, root. G root dot plus equal what?
Oh,
It's the same, what? G root plus equal what?
parent.
Yeah, it's easier. And now we just have to traverse the left tree and right tree, right? So can you tell me, DFS what? Root of what? Left. What's the parent of root of left? Come on, I asked you the question before. Yeah, we're done. Yeah, and another one, DFS what?
Root dot right.
And then, what's the parent?
Root.
We're done. And then we just call the beginning. DFS root. What's the parent of root?
Nothing.
None. Right, we're done. You see? You see?
One.
DFS search beautifully. Yeah, we traverse the tree in DFS search manner, recursion, but we need to pass down the parent, right? Because we need to add the edge from the parent to the root if there's a parent. Yeah. In the special case is the root doesn't have the parent, so we pass the none. If pass the none, the parent is none, and then it doesn't add the edge. Yeah. Okay, so that's a problem. Why is that? Look, I need to put it here, right? Because look, if there's a root still needs to add do I need to add that? Look. I pass down root. Okay, G root root adding the kids. No. Okay, wait. G parent, if parent, then parent adds to the root. Okay, and then the root needs to add the parent. No, maybe not. That's okay because in this case parent is nothing. Yeah, do you add you don't add the edge, right? So that's right. Yeah, because if it's the root, you only add the edge. You only go down to the kids to add the edge, right? So you go to the left and then you add the edge from 2 to the 1 or 1 to the 2. Okay. If parent is nothing, then we don't execute. So this is correct. That's the DFS search. And the breadth search. And how do we implement a breadth search? Do you still remember what kind of data structure are we using to implement the breadth search?
We're using Q.
What's Q?
It's thing.
First in what out?
Out.
First in first out. Yeah, it's like a queue, right? You wait in the queue, right? First come first serve. Yeah, first in first out. Okay. And in Python we use how do we implement it? How do we declare a queue? What? And then I need to put a root.
DQ.
Yeah, root. And the parent is none, right? The first parameter is the node. The second parameter is the second value in the tuple. Yeah, we're using the parentheses. Is the tuple. Is the parent. It's parent. And the DQ. DQ means tuple and DQ. Then while Q. Okay. So now we take an element out. So we take the current. We take the current and then we take the parent. And then that will be the same. Yeah. Q. How do we get the element? How do we get the element from the Q? How do we take it out? DQ. How do we take it out? Take the element out of the Q.
Pop left.
Well done, top left. From the left hand side. Yeah. If the stack is the other side, yeah, you pop, right? Yeah. Remember the stack. First in, last out. Yeah. You put this in and you take it out on the one side. But Q is different. Yeah. You DQ NQ. It means the putting an element into the Q. on one side and you take it out from the other side. This is pop left, this is append. Right? Why are we using the DQ? If we put it on the left side, if we put it on the other side, this is append left. Right? And then this is append left, pop left, append. And then this is what? Pop. Okay? Double NDQ means two ways you can do it. So one advantage of using double NDQ is that the operation, these four operations are all constant time, right? It's not like a list. In Python, if you declare a queue using this simple list, right? You can pop 0, remember? But pop 0 is linear time. It's called linear time, right? Alright? Make sense? Yeah? What did I just say?
Because linear time.
Pop 0, list called linear time, okay? So now we're getting the element from the queue. And then again, this is the same, yeah? If parent, well, what should we do? If parent, G, parent, append, current. Okay, can you tell me what's next? This is the same like before DFS search. G what? What? I added edge from parent to current. And what should I add in next?
Current.
Huh?
And that pat thing.
Parent, not pet thing, okay?
There is a pat.
Okay. Okay, and then if current dot left.
Said pat.
Okay, if current dot left, if there's the left kid, we need to push it into the queue, yeah? Append what? Can you tell me append what? Append a tuple, yeah? A tuple. So append current dot left, and then what's the parent of current dot left? What's the parent of current dot left? Current. And what should I do next? If what? If what? Yeah, push the left kid. What should I do with the right kid? Come on. Current dot right. If current dot right is empty, then we do this. Q dot append. Q dot append. Current dot right. What's the parent of current dot right?
Current.
Yeah. Okay. Okay, so what did I just talk about to sum up?
Binary trees.
No. You need to tell people that what have you learned today?
About trees.
And what's the problem we're trying to solve here?
We're trying to
Convert a binary tree to what?
into this.
This thing. What's this thing?
Is this
What's this thing?
dictionary graph?
Graph, yeah. What's that graph?
Undirectional graph.
And this is adjacent list, okay? It's all on the board, okay? All on the whiteboard, okay?
Yeah.
Okay, well done. That's it for today. Good job. Bye-bye. Bye-bye.
Yeah. Bye.
Show a happy face.
Bye.
That's not happy. Smiling.
Bye.
One more time.
Bye.
Okay, that's better. Thank you. Bye-bye.
Yay, finally.
Finally.